بسم الله الرحمن الرحيم. يسرنا جوستومون باش نقدموا الاكسبوزي الخامس الان موفقي خديجه من جامعه معسكر intitulé Biharmonic Hypersufaces in Einstein space and Conformally Hypersufaces.
بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Ladies and gentlemen, I am good morning. I am Khadija Mutore, PhD student from Mascara University. The title of my presentation is P-Biharmonic Hypersufaces in Einstein space and Conformally flat space. As an outline to my presentation, I will first begin with the introduction. Then I move the main results, which is divided by two subsections. Finally, the references. Introduction. In the introduction, we defined the P-Harmonic maps and P-Biharmonic maps. Let Barphy be smooth map between Riemannian manifolds. The P-energy function of Barphy is defined by the first equation, where is a compact domain in M. The Hypersmith knot of the differential D Barphy, e.g. the volume element on M, and P super or equal to smooth map is called P-Biharmonic if it is critical point of P-energy functional 1. We have here the bit de ce travail pour calculer le topic de field, the P-tension field. Let's number M the divisive with a conjunction of M, and number Barphy the feedback connection on value -1Tn. The map Barphy is P-harmonic if and only if the P-tension equals 0. Where the Toffee is the tension field of Barphy. The P-energy, the P-energy function of Barphy is defined by fourth equation. We say that phi is P-Biharmonic map if it is the critical point of the P-energy functional. The other Lagrange equation of the P-energy functional is given by this equation. Is defined the curvature, Riemannian curvature. Here we have the topic of Barphy, the tension, the P-tension, and the norm of Hypersmith. Well, its curvature tension defined by and number n, the differential connection of n, the P-energy functional, respectively P-energy functional and it's as a special case P equal to the energy functional, respectively B-energy functional whose critical points are usual harmonic maps, respectively Biharmonic maps. Autrement dit, si P égale à 2, le P-B-energy, si égale B-energy et le P-energy, linear energy. Submanifolds in a Riemannian manifold is called P-harmonic submanifolds, respectively P-Biharmonic submanifolds if the isometric immersion defining the submanifolds is P-harmonic map, respectively P-Biharmonic map. We call proper P-Biharmonic submanifolds P-Biharmonic submanifolds which is not P-harmonic. Now we move the main results. As already mentioned, it's divided by two subsections. The first subsection, P P-Biharmonic hypersurface in Einstein space. Let M be hypersurface. The hypersurface is a submanifold with codimensional one. And I, the canonical inclusion. We denote by number M, respectively number N divised without convection, or M, respectively of N, grad M, respectively grad N, the gradient operator in M, respectively in N. B, the second fundamental form of hypersurface. A, the shape operator with respect to unit non-vector field eta. H, the main curvature of M, number orthogonal, the normal connection of M. And by Laplacian, respectively Laplacian orthogonal, Laplacian is the Laplacian on M, respectively on the non-bundle of M in M. Under the notation above, we have the following results. Theorem 1. The hypersurface N with the main curvature vector H equal F eta is P-Biharmonic if only if F solving this system. Here, in the first equation, we have the normal party, and second equation, we have tangent party. Where Lick, respectively Ricci, is the Ricci curvature, respectively Ricci tensor of to prove this theorem, we have to calculate the p-bit tension of I, of canonical inclusion. After the calculate, we find the system. As an immediate consequence of theorem 1, we have a hypersurface M in Einstein space is P-Biharmonic if and only if its main curvature function F is solution of the following PGDs. In the proof, where S is the scalar curvature of the ambient space. In the proof, here we used the definition of Einstein manifold. We say the manifold is Einstein manifold when dic xy equal lambda metric on xy. For some constant lambda is called constant of Einstein or Einstein constant. For any xy in gamma Tn, so that S the full base of scalar equals raise Vic. They are totally umbilical hypersurface M in Einstein space N with no positive scalar curvature is P-harmonic if and only if it is minimal. Stadio F equals 0, minimum. H equals 0, we have H equal F eta, so F equals 0. Here take orthonormal plane EI eta. The EI is plane in space tangent, and eta is normal. On the ambient space, such that is orthonormal plane on M, we have. Here we use the probability of umbilical hypersurface. The second fundamental, we find F equal beta, where beta is a smooth function in M. The P-Biharmonic hypersurface equation equation set become like that. Solving the last system, we have beta equal 0 and hence F equals 0, or beta equal square S divided by the positive number. It's a constant, and this happens if only if S positive. And in the theorem, we suppose that S negative, non-positive. The proof is complex. Here we passed in the second subsection. P-Biharmonic Hypersurface in conformally flat space. Let I, the canonical inclusion, be minimal hypersurface. IT. Here we deform the metric. When we deform the metric, the connection, the tensors, all are deformed. Conformally flat space is space with the new metric. La déformation paramétrique. Theorem 4, the hypersurface amplified in conformally flat space L m plus 1 H-type is P-Biharmonic if and only if the system gamma solving the system, where G-type equals exponential gamma fois G. Exponential to gamma. Where Lucian is the Lucian of the smooth function gamma in Ln plus 1. Here we قال لكم بدنا ما ديفورماسيون نعملوا نسبوها لكم السيستم. Remark or objective of the second section. Using theorem 4, we can construct many examples for proper Biharmonic hypersurface in conformally flat space. Because we know that on a plusieurs exemples. La métricale se forme, par exemple, J égale F, la métrique standard, c'est-à-dire le produit stable. To simplify the calcul. If function gamma and eta gamma are non-zero constant on M, according to theorem 4, the hypersurface is P-Biharmonic in Ln plus 1 if and only if the norm locally of A equal this quantity. As an illustration, we have the following examples. The hyperplane in Ln plus 1 with the metric exponential 2 gamma z h, where gamma is a smooth function and h is a standard metric, and c in L is proper Biharmonic if and only if 1 minus p gamma gamma la dérivée de gamma point c au carré moins la dérivée deuxième au point c égale à 0. Note that the smooth function gamma z equal this number is the solution of the previous differential equation. Example number 2. Let M be surface of revolution in M3 with Z positive. If M is part of a plane orthogonal to the axis of revolution, so that M is parameterized by this parameterization for some C superior to 0, here Fx superior to 0, then M is minimal, and according to the theorem 4, the surface M is proper Biharmonic in three-dimensional hyperbolic space. And then we have open problems. If M is minimal surface of revolution contained in catenoid. That is n is parameterized by this parameterization, where a and b are constant. Is there p superior or equal to and gamma in gamma smooth function in R3 such that n is proper Biharmonic in R3. It's open problem. Is there proper Biharmonic submanifold is integrated in Euclidean space? And finally the differences. Here the difference number one, only harmonic and P-Biharmonic maps. Le champ de P-Bitension on voit les attaques serrage d'Ita. Quand on a serrage KTA, en 2018. Ouais. Quand on déjà travaillé avec le champ, thank you for your attention.